you ever stop and think about it? How doctors can look deep inside your body, see all its secrets without ever making a single cut? Well, today we're going to take a guided tour of that incredible world, medical imaging. I mean, how do they do it? How do you get this crystal clear picture of your bones or your brain or even your heart beating in real time, all from the outside? It really does feel like magic, right? But it's not. It's just pure, brilliant physics. And really, to get our heads around it, we just need to understand two basic toolkits. Think of them as two totally different ways to tackle the exact same problem. How do you see the invisible? All right, so let's crack open that first toolkit. This one is all about using energy to create pictures. We're talking about a specific kind of high energy called ionizing radiation. Now, that sounds a little intimidating, I know, but it's the foundation for some of the most common scans you've ever heard of. So, what is it? Well, picture this. High-energy waves like X-rays come flying in and literally bombard an atom. They've got so much oomph that they can physically knock an electron right out of its orbit. Boom! Now, that atom has a charge. It's been ionized. And that one little interaction, that's the whole secret sauce. That's what lets us build an image. And the granddaddy of them all, the original and most famous use for this, is the good old X-ray. You know, the easiest way to think about an X-ray? It's basically a super high-tech shadow puppet show. Seriously, we're shining a special kind of light through the body and just capturing the shadow it casts. But how does that shadow get all its detail? Well, it all comes down to absorption. Or if you want to get fancy, physicists call it attenuation. It just means how much different parts of your body block the X-rays. Think about it. Dense stuff, like your bones, they're great at stopping X-rays. So not many get through to the detector on the other side. That's why bones show up as bright white on the film. But your soft tissues, they let a lot more of those X-rays just sail right on through, which creates the darker grayish parts of the image. That difference, that's the contrast. That's what lets us actually see things. Okay, so if the X-ray is the classic, the CT scan is like the supercharged 3D sequel. It takes that same basic idea and just launches it into a whole new dimension. Instead of one flat shadow, a CT scanner spins an X-ray tube 360 degrees all the way around you. And as it's spinning, it's snapping hundreds of pictures, these super thin cross-sectional images. It's just like looking at individual slices of a loaf of bread. Then the real magic happens. A computer takes all of those 2D slices, stacks them all up, and builds a complete, detailed 3D model of your insides. It is absolutely incredible stuff. But what if we totally flipped the script? You see, with X-rays and CTs, we're shooting energy at the body. But in nuclear medicine, we do the complete opposite. The patient actually becomes the temporary source of the signal, and we have a special camera that just listens. So how does that work? Well, a tiny and very safe amount of a radioactive tracer, called a radionuclide, is injected. A really common one is technetium-99m, which is great for things like bone scans. This tracer is super smart. It's designed to hitch a ride through your bloodstream and collect in specific organs or tissues. And as it naturally decays, it sends out little signals, gamma rays, that a special gamma camera can detect. The result is an image that shows not just what your organs look like, but how they're working. It's about function, not just form. Now, of course, anytime we're talking about radiation, the number one question is safety. And in medicine, it is the absolute top priority. The whole philosophy is guided by something called the ALARA principle. ALARA stands for as low as reasonably achievable. It basically means that doctors are required to use the absolute smallest dose of radiation they can while still getting a good enough picture to make a diagnosis. It's always a careful balancing act between the medical benefit and any potential risk. Okay, let's put that first toolkit aside and pick up our second one. This is where things get, well, really clever. This is where scientists and engineers figured out some truly ingenious ways to see inside us that have nothing to do with ionizing radiation at all. First up, ultrasounds. And the key thing to know here is it has zero to do with radiation. It's all about sound. The machine sends out these super high-frequency sound waves way above what any human can hear. These waves travel into the body, and when they hit the edge of an organ or a different kind of tissue, some of them bounce back as an echo. The machine's probe then listens for those echoes, times how long they take to return, and uses that information to build a live picture. It's literally sonar for the human body, just like a submarine. So why would you use ultrasound? Well, its biggest superpower is that it's live. It's happening in real time. You can watch a heart valve flapping open and shut, or see blood flowing through a vessel. Speaking of blood flow, it can even measure its speed and direction using the Doppler effect. You know, the same thing that makes a siren change pitch as it passes you. And most importantly, it's considered extremely low risk. The things they watch out for aren't radiation, but just tiny amounts of heat or the possibility of creating microscopic bubbles, which is called cavitation. That's why the person doing the scan is always monitoring these safety numbers on the screen. And that brings us to the undisputed heavyweight champion of soft tissue imaging, the MRI. Magnetic resonance imaging. This one is really in a league of its own. No radiation, no sound waves. Instead, it uses two things: a ridiculously powerful magnet and pulses of radio waves. And what it's doing is listening for the teensy tiny signals coming from the protons inside all the water molecules in your body. So let's try the simple version of how this crazy thing works. First, that giant magnet, it makes all the protons in your body line up, like tiny little soldiers all pointing in the same direction. Step 2, the machine sends in a quick pulse of radio waves. This knocks all those little soldiers out of formation. And here's the magic part, Step 3. When the radio pulse turns off, the protons relax and snap back into alignment. As they do that, they give off a faint little signal. The scanner's coils are basically super sensitive antennas that listen for those signals, and a computer uses them to build an unbelievably detailed picture. And this gets to the main safety issue with an MRI. It's not radiation. The big deal is that magnet. It is always on, and it is thousands of times more powerful than the Earth's magnetic field. The main danger is something called the projectile effect. Any metal object that's magnetic, we're talking anything from a paperclip to a wrench to an oxygen tank, can become a deadly missile, pulled into the center of the magnet at incredible speeds. And that is why they are so strict about screening for any metal before you go anywhere near that room. Okay, so we've got our two toolkits, one based on radiation, the other on other kinds of clever physics. So how on earth does a doctor choose which one to use? Well, like any good craftsperson, it's all about picking the right tool for the specific job you need to do. Let's just run through it. If you need to spot incredibly tiny details, like microcalcifications in a mammogram, you want the super high resolution of low-energy X-rays. If someone comes in after a major accident and you need a fast, detailed 3D map of their bones and organs, CT's the king. But if you need to see the subtle differences between soft tissues, say in the brain or in a knee joint, nothing, and I mean nothing, beats the amazing contrast of an MRI. For anything that's moving, like a baby in the womb or blood flowing through an artery, the real-time, safe nature of ultrasound is the obvious choice. And finally, if you don't just want to see what something looks like, but what it's doing, like finding a metabolic hotspot, that's a job for a PET scan with its radioactive tracer. Ultimately, the choice often comes down to two key ideas: resolution and contrast. So, resolution, that's just about detail. Think of it like the megapixels on your phone's camera. Can you see two tiny little dots as separate, or do they just blur into one blob? That's resolution. Contrast, on the other hand, is all about telling things apart. Can you see the difference between two types of tissue that are right next to each other? That's why an MRI, with its jaw-dropping contrast, is so good for the brain, while a mammogram, with its incredible resolution, is perfect for spotting those tiny specks. So, where does all this go from here? What's the future look like? Well, it's not really about picking one tool or another anymore. The future is all about bringing them together. And this is where we enter the world of hybrid imaging. The perfect example is a PET CT scanner. It's one machine that does two scans at once. The PET scan is brilliant at showing function. It'll show you a hotspot where cells are really active, but it's kind of blurry. It's not great at telling you exactly where that spot is. That's where the CT scan comes in. It provides the perfect high-res anatomical roadmap. So you fuse the two images together, and boom, you get the best of both worlds. You can see the functional hotspot from the PET scan overlaid perfectly on the anatomical map from the CT. It's an absolute game changer for diagnosis. And that kind of leaves us with one last big thought. Think about it. In just a little over a century, we've gone from blurry black and white shadows to seeing real-time 3D functional maps of our own bodies. And now that these amazing toolkits are actually merging and getting even more powerful, well, the future isn't just about treating what's wrong. It's about understanding the human body in ways we're just beginning to imagine. It just makes you wonder, what invisible secrets are we going to uncover next?